right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. Thank you for tuning in. We're going to go ahead and jump right into it today. I've got a lot to get to you. We're going to take a look at summation of reactions and using the summation of these reactions to actually calculate an enthalpy value. Now, I've got a statement written here on the screen immediately that enthalpy is a state function, and I think it's really important that you understand the whole concept or idea of what a state function is. If you want to put it in relative terms, something you're probably familiar with, think about if you go to a high-rise building, and I've got, let's say, 15 or 20 different floors in the high-rise building. If I want to go from floor 1 to floor 5, it doesn't matter how I get there. The difference between going from floor 1 to floor 5 in elevation is always going to be the same. That does not... It doesn't matter if I go from floor 1 to floor 10, then back down to floor 5, or if I go from floor 1 to 2, then to 3, then to 4, then to 5, or if I take the elevator, or if I take the stairs. The difference in elevation from floor 1 to floor 5 is exactly the same no matter how I got there. All right? And so that idea is the idea of a state function. It doesn't matter where I go or how I get there. It's just where I begin and where I end. All right? And so the other thing that I definitely want to make sure that you understand is the fact that enthalpy is actually a molar value. And what that means is, because we are going to get to the point with these reactions where we are going to start multiplying and dividing these reactions to change coefficients, and you have to understand if we multiply or divide or we change these coefficients, we are going to change these enthalpy values because the enthalpy values are based on the number of moles shown in the particular reaction. And if we change that, we change the amount of heat that's going to be absorbed or released, all right? Okay, so now let's look at a very diagrammatic way to think about reactants and products. So if I'm going just straight from reactants to products and we're just moving right there, one step, nothing in the way, that's essentially what we're going to call the enthalpy, right? That's the change in thermal energy that it's going to take from getting to reactants to products. Now, something that we also have looked at in this particular class thus far is we can still just go reactants to products, but what we can also do is we can tear down these reactants to their elemental form, right? And then we can come up and calculate that value, right? I'm still looking at a delta H, but in this particular case, going from the breakdown here, I'm going to use my enthalpy of formation values, right? Because these are going to be breaking down to my elemental form. And remember, my formation reactions are going from the pure elements to a mole of substance, right? So going the reverse would be taking me down to my elements. And then on the other side, so this would be for my reactants, and on the other side, we can use the same enthalpy of formation values for my products and actually add everything back up to take it from its elemental state back up to the products that are formed, all right? And again, this works. It doesn't matter that I have to come down to the elements and then come back up to the products because by definition, my enthalpy is a state function. It doesn't really matter how I get there. It's just the change from reactants to products, and this actually is the basis, right? The enthalpy of reaction is equal to my enthalpy of formation values of my products minus the enthalpy of formation values of my reactants, and those are sums there, all right? And maybe I should just go ahead and put that in there. So just squeeze in a sum mathematical formula, all right? Okay, and so now what I'm going to do is I'm going to take us to where we're at, where I'm still going to be looking at products to, reactants to products. We're still going to be looking for this overall enthalpy of reaction value, but in this particular case, what we're going to do is we're going to come down here and we're going to go through a series of reactions, right? I'll have reaction 1, and then from reaction 1, I can also get reaction 2 to occur, and then I can get reaction 3 to occur, and this can go on for as long as we want, and then from those reactions, we can actually end up with an overall set of products, right? It's still the same thing. It's just like using enthalpy of formations as long as I can actually just sum up. So summing my reactions here also works because of the same reason that those enthalpy of formation values works, is that enthalpy is a state function. So I can actually add these reactions up and still end up with reactants and products of an overall reaction. Now this is very similar to, think about when we did our electrochemistry, where we were taking our half reactions, we would add two half reactions together, certain elements of that would cancel out because it was redundant on one side of the other, and then we would end up with an overall reaction that just showed exactly what was left over, right? So this is not a stretch for a lot of people, hopefully, if you can remember back to those electrochem days, all right? Okay, and so a situation where we might run into this is where we have a target reaction, and for whatever reason, we can't actually get the reaction to occur in one step. We've got to get a series of reactions to get this to happen, and what we can do is we can calculate the overall enthalpy or energy exchange based on looking at the half reactions that we know. All right, so in this particular case, what I'm going to do, and I've left this open down here, my target is normally given to me early on in these problems, right? And then they give me this series of steps that I can follow to get the overall. But what I need to understand is this works just like an addition problem. I need to take my target reaction and actually rewrite it down below, right? Because this is what I want to make sure that I align and line everything up with. So what we do here is we just start trying to get everything on the right side or on the correct side. So what I always do is I start with my my products, I'd start with 2NO2. Now look at my half reactions up here, or my series of reactions, and I'll notice that NO2 is actually a reactant on here. So what I've got to do is I'm going to take this, draw a line through it, and I'm actually going to flip that whole reaction. So I'm going to rewrite it as O2 plus 2NO is going to give me 2NO2 as a gas. And so now, notice I've got, number one, the coefficients is correct, but now I'm also on the correct side of the equation. Now the other two elements I've got to look at here are my oxygens, right, and my nitrogens. Now I notice my oxygens are on the same side here, right, and they're on the reactant side. They're correct, and my coefficients add up to 2 because I've got 1 plus 1 here. So I've got 2 moles of oxygen on my reactant side, and then nitrogen comes down, I've got 1 mole. So in this particular case, I've got it ready. Now notice I flipped the reaction here, but I did not do anything to the enthalpy value here, and that was my mistake. I should actually make that a negative 112 kilojoules, right? Because I flipped the reaction. This is a state function. I'm just going in the opposite direction. So the sign of my enthalpy value will be reversed. And so now to come up with the overall, like if I wanted the delta H for my overall target reaction, all I do is I just add these up. So now I'm 180 minus 112, and I end up with 68 kilojoules of energy, and this would be an endothermic process. All right, and so another example that I'm going to do with you here, again, I've got just a couple of steps of reactions or a series of reactions that I want to add together to come up with an overall target. And so again, I just want to make sure and emphasize that we're going to put our target reaction, just like we're going to try and add these things up, down at the bottom. And again, it's just to make sure that everything lines up on the correct side of the equation. So again, first thing I'm going to do is I'm going to start taking a look at my products. So NH3, I'll notice that NH3 is over here on the reactant side, so I'm going to have to flip it, but then also I notice that the coefficient is incorrect. In my series of reactions, I'm showing as 2 moles of NH3, and then I actually only need 1. So I'm not only going to have to flip this reaction, I'm also going to have to divide it by 2. And so what I'll do is I'll actually just cross right through that thing, and I'll end up with 3 divided by 2 H2, because again, I'm just dividing by 2, right, plus 1/2 N2, and again, that's just 1 divided by 2, and then 2 divided by 2 gives me just 1 mole of NH3. So now I've got NH3, right? Put a check mark next to that. I've got the proper number of moles there, right? And now I need to make sure that I come over here and I'm going to correct this. So this would be negative 92 divided by 2, which equals negative 46 kilojoules. So again, this goes back to the case that enthalpy is a state function and the fact that it is a molar value. If I change the moles, I change the overall number. So since I cut all the coefficients in half, I should actually cut my enthalpy value in half as well. Okay, so the next thing I'm going to do is I'm going to start looking at the water, and again, I see water is on the wrong side, but my coefficient's correct, so I don't have to multiply or divide by anything. So I'm actually just going to flip this, so I end up with 2H2 plus NO2 is going to give me nitrogen plus 2 waters on the other side. All right? And so at this point, I know it gets kind of confusing, but I just want to add up and make sure that everything ends up on the proper side. Let's see, what did I end up with here? Nope, you know what? I just realized that I actually left off a coefficient here. This should actually be 1/2 N2 to begin with. If you'll notice, I've only got one nitrogen on the other side of the reaction, so that's my fault there. But what that does, and where I got tripped up here, is I was looking and I was noticing that my nitrogen was not going to actually cancel out, right? Because I've got my NH3 coming down, I've got my 2 waters coming down, so I'm good there. And then my nitrogens, I actually should end up with these guys canceling out, and I do, since I've got both reactants and products, right? The next thing I'm going to look at is this tricky hydrogen here. I've got 3/2 plus 2. Well, if you think about that and actually add it up, that does add up to 7/2. And so go ahead and refresh yourself with working with fractions. So this actually ends up with 4/2. So 4 plus 3 is 7/2. And then my NO2 actually comes down and is okay there as well. So I end up with my target. I flipped this reaction. So again, you can't remember, or you can't forget to go back and change your enthalpy values here. So I should end up with a negative 170 kilojoules. And so my delta H of my overall reaction is actually equal to negative 216 kilojoules. And again, this is all based on the fact that your enthalpy values are state functions and the fact that they're molar values, right? It doesn't matter how I get there. It's just difference between starting and ending point there, okay? All right, ladies and gentlemen, that's it. If you had some questions, hopefully you got them down. We'll get them taken care of in tutorials. And other than that, I'll see you in class.